Now we're going to look at example 8, which is from your notes packet. So if you don't have your notes packet open, then you should get that in front of you. I, again, made a short video to insert into this video because then we have a meta video, and that's awesome. So if you don't have it out, you should probably pause it. All right, let's see. I've written some things already, so let's talk about some of those things. Up here, it's describing the charged object as a charged insulating sphere, and above that I've indicated rho. Well, how do I know it's rho and not something else? Well, the implication by not mentioning the word hollow is that it's a solid object. I realize maybe I'm kind of reaching, but if you look down to part A, it asks for the charge density in coulombs per cubic meter. So that would seem to imply that it's a solid object. They wouldn't be asking for the density in coulombs per cubic meter unless it were a solid thing. Okay, so if it were hollow, it would probably mention the word hollow. Also, the fact that it says that it's insulating is crucial here. If it were a solid metal sphere, the fact that it's a solid would actually be pretty unimportant, right? If it were a hollow metal sphere or a solid metal sphere, conductors, the charge always lives on the outside. So in either case, you'd be talking about sigma, not rho, right? Charge would just be on the surface, not buried in the middle. Okay, let's let it go a little bit. You can see I've written rho equals Q over V, and we're just getting into the nitty-gritty of plugging in numbers for that. Oh, look at that! There's a geometry equation that you might remember. 4/3 pi r cubed. We're actually going to need to know a few geometry equations, so I'm going to write them down here, and then some of these you'll use in the next example. And you may not use all of them in the 3 examples I had you work out, but you're going to need to know the volume and surface area formulas for things like cylinders and spheres. So volume of a sphere, I've already got written down there on the screen, but I'll put it up here. 4/3 pi r cubed. Okay, so that's the volume of a sphere. On the other hand, if we had, like we said, like a metal sphere where the charge was on the surface, we would probably want to know the surface area of that sphere. So the surface area of a sphere, if you're in calculus, it's actually the derivative of that. If you're not in calculus, then you don't know necessarily what that means, or at least you wouldn't find a derivative in your head. But oh, goodness gracious, oh no, I messed up and I meant to write r. There's an r there. Okay, so it's 4 pi r squared. The r is squared. Okay, so surface area of a sphere. Next, if you're dealing with cylinders, volume of a cylinder, you probably remember the formula area of the base times the height works for any prismatic solid. So for a cylinder, the area of its base is pi r squared, and its height, I'm going to usually call it, instead of height, I'll call it length. The reason why I'm doing that is going to be made much more clear later on in the unit when we get deeper into Gauss's law. But instead of height, I'll usually write the length of the cylinder. Surface area of a cylinder, you're also going to need to know. A little bit of explanation on that one since I think it merits it. Surface area for a cylinder, if you imagine taking a cylinder, that's a poorly drawn cylinder, right? But if you imagine taking a cylinder there, and if it's, say, I don't know, a can with a label on it, and you cut that label off like that, and you lay it out flat, it's a rectangle. It's a rectangle with a width of however tall the can is, and a length of the circumference of a circle. So that means that the surface area, the lateral surface area of a cylinder is going to be 2 pi RL. And most of the time, we're going to ignore the end caps, meaning the 2 circles that are on the top and bottom of the cylinder. Some problems, they might include those, so you have to read closely. Okay, but most of the time, ignore the end caps. They're not going to matter too much. All right, let's let this play. All right, typing things in, and there's the charge density. Notice something while I'm writing there. I converted the radius from centimeters to meters. You're always going to have to do that. Like with most things in physics, centimeters aren't actually okay when you're plugging into equations stuff. So meters. Okay, the second part of that question wants to know the fraction of the sphere's total charge that exists within a particular radius. That's a question where it's maybe not necessarily important of itself, but is important because it demonstrates it demonstrates the use of a few different formulas and also of a use for density. If we're talking about the whole sphere versus just part of the sphere, all parts of it have the same charge density because it says it's uniformly charged. So if you figure out, okay, how much charge is in here versus how much charge is in the whole thing, that fraction would be, we're going to call it little q in here, and big Q is going to represent all of the thing, and little q over big Q is going to be the fraction of charge that exists within a particular radius. All right, so here I am writing that the density for both spheres is the same. That's all that means right there. Q over V equals Q over V. Okay? All right. And then there's that fraction little q over big Q I talked about, which is the fraction of the total charge which exists within a particular radius. All right, pause for a moment. What have I done? Well, I have done a little bit of algebra. If we're solving for little q over big Q, that means I'm dividing both sides by big Q. There goes the big Q to the bottom because I just divided by it. And little q over big Q then is going to equal that right there, which I get by multiplying both sides by, I called it V r over 2, meaning the volume of the sphere that exists at half the radius. Okay? All right, right here we got going on 4/3 pi r cubed over 4/3 pi r cubed. All right, but the top one, that's the smaller inner sphere we're talking about. The 4/3 pi's, those are going to cancel because for both objects, okay, fractions of the objects, whatever, it's a sphere. All right, there. So notice the answer is 1/8. If you were thinking the knee-jerk reaction of, oh yeah, half the radius is going to be half the charge, not so much, because if you recall, the volume of a sphere is proportional to r cubed, right? So what that means, since it's r cubed, is that if you had a sphere with half the radius, it would have not half the volume, but 1/8 the volume. If it's got 1/8 the volume, then it's going to have 1/8 the, in this case, charge. Okay. Well, that's all. I think you should be able now to move on to the other examples. That's the remainder of your homework. Let me know if you have any questions. You could always email me if you're not sure exactly what you're supposed to be doing. Thanks very much. I hope that was helpful.